Hello, today our lecture will be the continuation of the previous lecture. Previous lecture I was discussing about the plate girders. In fact, as I was telling, the plate girders has several components, so it is very difficult to discuss all the things in a short period. So, today I will give the remaining part of the plate girder things, right. So, last day up to the design of flange of the plate girder has been discussed. Again, plate girder means two type of plate girders are there. One is riveted plate girder, riveted jointed plate girder, and another is welded jointed plate girder. So, I was discussing about riveted plate girder. So, here some components I will exclude from riveted plate girder and I will discuss in case of welded joint plate girder. Some components means I have showed yesterday, means last lecture, that what are the components are required to design a complete plate girder. What are the components? Let us just have a look. That is, say one is calculation of external load and estimation of self weight. This we have discussed, right, and calculation of shear force and bending moment. Then deciding the depth of plate girder, then design of wave plate, and then design of flange. These are the things which we have discussed. Now, we will discuss remaining part like curtailment of flange plate, and then design of connection between flange plates and wave, and design of connection between the flange plates and angles, design of stiffeners, design of wave splices, flange splices, and end connections. So, some of this part we will discuss with reference to riveted plate girder, and some of them we will discuss later in case of welded plate girder, which are similar almost, right. So, first we will discuss about the curtailment of flange plate. Why curtailment is required? In fact, in case of discussion of beam design, there I have shown how the curtailment has been derived, means curtailment length has been derived, and how it is affected to get economic design, right. Just let me give a small overview. Say this is a beam. If we see what will happen now, why curtailment is required? Because if we have a huge load, then say suppose we have a UDL load, then how the bending moment will develop? Bending moment will develop, bending moment will develop like this parabolically, right. So, the maximum moment is developing here, maximum, right. Now, when we are going to design the plate girder, we generally design with the maximum moment. So, on this basis we are going to design, and on this basis we are going to provide the additional plate, right. Additional plate we may be going to provide, right. But this much additional plate is required in this section, but is it required here? Because the moment is less, as it is parabolically varying, so moment is going to less. So, is it really required here? So, it is not required because moment is less. So, because the section modulus is nothing but m by sigma b, right. Now, section modulus will be less if m is becoming less. So, what we can do? We can make some curtailment, maybe after some distance we will provide up to this only. Say first plate will provide throughout. In generally plate girder we provide one plate we provide throughout, then say we can curtail here. That means here these portions we are not going to take, this portion we are not going to take, right. Then maybe here maximum is there, so we are that plate we are cutting here, right. So, this will be another plate. So, in this way we can make a plate girder with heavier section at the middle and lighter section at the side, and we can reduce the depth of the plate girder towards the support if it is simply supported beam, right. So, in this way we can make. Now, generally the first flange, as I was telling, first flange cover plate are carried through the length of girder to serve the following purpose. What are those purpose? One is it ties together the outstanding legs of the flange angles. It ties together the outstanding legs of the flange angles. And second is a top flange with first cover plate coupled may allow rainwater to collect between the flange angles and the wave, resulting in corrosion. So, for these two reasons, generally first flange cover plate are used throughout the span. The length of curtailments of plates can be found conveniently by algebraic method or graphical method. There are two methods we have, one is algebraic method and another is graphical method, through which we can find out the length of curtailment, right. Now, let us first discuss about the algebraic method. In case of algebraic method, say let us consider say A dash F is the net area of flange. That means net area of flange means flange angle plus flange plates. Net area means the area minus rivet hole, right. And let us consider A1 dash, A2 dash, like this AN dash are the net areas of first, second and nth cover plates respectively counted from outside. So, A1, A2, A3, A4, the number of plates how many we are going to provide, we are giving them name as A1 dash, A2 dash, AN dash, like this, means plate area we are considering like that. So, as the effective depth of the plate girder is approximately same even after curtailment of flange plates, it is therefore assumed to be same throughout the span. If the girder is subjected to a uniform load over the entire span, the bending moment diagram is parabolic, as I was telling. In that case, what will happen? We know bending moment will become, so WL square by 8, maximum bending moment will become WL square by 8, and that has to, this is the external moment which is coming, has to be carried by the plate. So, moment of resistance will become sigma Bt into A dash A plus A dash W1 into D1, right. The terms which already we have used in last lecture, similarly we will use here, right. Now, we can write also WL square by 8 minus W into 2xn whole square by 8 is equal to this sigma Bt into A dash F plus A dash W1 minus A1 dash plus A2 dash plus up to N, where A1 dash A2 dash I have told already net areas of respective cover plates, and x1, x2, xn are the distance of the cutoff points from the center of the plate girder. I will show the figure, right. So, xn for the nth plate, the distance from center to the cutoff points. So, this we can write in this way, right, sigma Bt into A dash F plus A dash W1, this is the total, minus A1 dash plus A2 dash like this into D1, right. Now, if we divide equation 2 by equation 1, then what will happen? We will get this type of equation. That means 1 minus 2xn whole square by L square is equal to 1 minus A1 dash plus A2 dash plus up to AN dash by A dash F plus A dash W1, right. So, the equation can be made in this way. Now, if we further simplify, this can be reduced from both the sides. So, what will happen? X n 2 x n by L will become root over this a 1 dash plus a 2 dash plus up to a n dash by a f dash plus a w 1 dash. So, this will become like this. So, 2 x n by L. So, from this I can find out x n. So, what will be the x n value? X n will become L by 2 square root of this whole square root of a 1 dash plus a 2 dash plus up to a n dash by a f dash plus a dash w 1. Now, these are the area of plates, summation of area of the plates. So, from this equation, if number of plates are n, then the length of x 1, that is the distance of the cutoff point from the center to that plate girder, that x n can be find out from this equation. So, similarly, if we consider about x 1, then we can find out the equation like this, that will be L by 2 into a 1 dash by a 1 a f dash plus a w 1 dash of square root. Similarly, x 2 what will be? X 2 will be L by 2 into square root of a 1 dash plus a 2 dash by a f dash plus a w 1 dash, right. So, in this way x 1, x 2, x 3 whatever number of plates are there, we can find out their length, right. So, by algebraically we can find out easily, right. Now, the similar way we can find out from graphical method also. In graphical method, what we will do? Say there is a, suppose there is a beam, right, having a urea load, and this is the first plate which is given, means flange, this is the flange, right. So, what will happen now? Now, we can provide a, as we told that first plate will be provided throughout the span, this generally we used to make, right. Next, we will provide some other plates. How do we provide? Let us see. So, for that what we have to do? We have to take some graph paper from which we can find out. Means first we will find out, because of this simply supported beam with having L length, what is the maximum moment, right, that is W L square by 8, if W is the UDL load acting on the beam. So, the moment will develop like this, right. So, this is the maximum moment which is developing, I can write M max, right. Now, what we will do? In graphical paper we can, means we can make it scale, a suitable scale we can use to scale down the or scale up the results, means the moment we are making here, right. Now, again what we can do? We can write down the area, say a line we can keep, and area of each flange can be written. First is the original area, which is, say suppose it is here, right, this is the O, say let us consider say x, not x, say P, right. So, this is the original area, means that is given, no, A f dash plus A, means area of flange, right, area of this is the area A dash f plus A dash W 1, right. A dash W1 plus A dash F, right. Now, other area A1 A2 means of the plate we can scale like this, say other area is like this, right. So, we can give their name, say the outsider one means the last one here, let us put say A, okay, right. Now, let us join with this, the maximum one with this, the outermost one. So, this is got like this. Next what we will do? Next, for another plate, this is say another plate area, say A1. So, this is parallelly we will make, parallelly we will go, then again horizontally we will give here, right. Then if we make like this and if we go down, so this will be the plate which we have to provide, right, and with some outstanding length, because whatever required is there little higher to accommodate the rivet etc., right, for connections, right. Again for this it will be parallelly we can take this and like this, right. Okay, first I did a small mistake, first let me take this one. So, this will be like this, right. So, the first plate will be up to this, right. So, this is the first plate and second one is here. So, second one I am considering this one, right. So, second one is like this. Then in between if we want to provide some plate, so suppose some other plate is there, then their cutoff point also can be find out from similar way. Say this will be the cutoff point, right. So, in this way another plate we can provide, okay. So, this is how by graphical method also we can find out the cutoff length. However, better way is to do from the algebraic formula, because formula is there, from formula we can get x1, x2, x3 very quickly, right, and the actual length whatever we will be providing will be little higher side from the theoretical one, right. So, this is the way how to find out the curtailment of the flange. Next, we will discuss about welded plate girder. The remaining component we will be discussing in welded plate girder. As we told earlier that plate girder is of two types, one is riveted plate girder, another is bolted plate girder, welded plate girder. Bolted plate girder also is available, which is similar to riveted plate girder, right. So, in case of welded plate girder, the difference is that here because of absence of hole, because the rivet is not there, so there will be no deduction of area. So, net effective area is not going to reduce from the gross. Therefore, the efficiency of the welded plate girder will be more, right. The strength of the welded plate girder will be more. So, this is the difference, and now we will see how to find out the effective depth, means economic depth and economic size, how to find out. In case of riveted plate girder we have seen, here we will see which is little different, means in a different way we have to do, and other things like connections etc., as we know how to make that for riveted connections. Say like we have to see what is the rivet value and what is the forces is coming, then we have to find out number of rivets, then we have to find out pitch etc., So, those means usual things I have not discussing here, right. In case of plate, little in case of weld, little more I will discuss about those things, those connections, etc. right. So, first let us see how does it look. The normal section is generally just simple section what I have shown last day, that is simply the girder is made with the plate, solid plate. This is the plate, the wave plate, plate for wave, right. Now, here it is welded, here it is welded, right. These are in general normal section we can say. Another section also I have shown, that is called hybrid girder. That means we can take it from some rolled section, right, maybe from T section, right, and then by the use of butt weld we can go, then again some another T section or some other section, right. This is basically cut from wide flange section, right, and this portion is generally lower strength, right. These are lower strength wave, and this is called hybrid girder. This is called hybrid girder. Two other sections I will show which is used in bridge mainly. This section is very commonly used in bridge, that is box girder, right, box girder. So, how does it look? This is like this. That means there is a plate, solid plate which is forming like a box and welding here at the joint to make this box. This is called, right, box girder, and this improves torsional stiffness. This section improves torsional stiffness, and these are useful in case of longer span. If span length is very high, then generally we used to provide box girder, longer span, right. Another type of girder, welded girder we use, that is called delta girder. This will be looking like this, right. This is called delta girder, that is this will be stiffened by like this, means it will be joined like this, and this will be joined like this, right. So, this is called delta girder, right, and this improves the lateral rigidity, improves lateral rigidity. The advantage of this is to improve the lateral rigidity. So, these are some typical welded connected plate girder, right. Now, first let us see about the wave. How do we design, means how do we decide the wave, right. the depth of the section of the wave is usually taken as 1/8 to 1/12, 1/8 to 1/12 of the span, right. The depth of the section generally we choose at the beginning 1/8 to 1/12 of the span length. The wave is designed for shear. As we know, flange are taking care moment and wave are generally taking shear. So, wave has to be designed for shear. The wave plate should be designed against local buckling. It should have adequate strength to carry shear force, and the average shear force in the wave, as we know, is tau v cal, that can be find out as V by dw into Tw. We know this formula already we have used, and it should be less than tau Va. Tau Va is the permissible shear stress, right. That also given in the code, tau Va, the permissible shear stress, that should be 0.4 Fy. This is for unstiffened wave, and for stiffened wave the value is given at table 6.6a of IS 800/1984, right, for Fy 250, right. And other as usual, like Tw is the thickness of the wave, Dw is the depth of the wave plate, and V is the maximum shear force on the girder. V is the maximum shear force on the girder. So, from the shear force point of view, we have to check the depth whatever we have considered, we have assumed that is 1/8 to 1/12, whether that is sufficient or not from shear point of view. And how do we check that permissible stress? Either it will be 0.4 Fy for unstiffened wave, and for stiffened wave the value is given in the code in IS 800/1984 in table 6.6a. Now, we will go for the flange. In welded plate girder, since there is no hole in tension flange, the total effective flange area will be given by this, F is equal to m by sigma bt into dE, where m is equal to maximum bending moment in the girder. M is maximum bending moment in the girder, and sigma bt is the allowable tensile stress in bending, and d is the effective depth of wave. So, effective area of flange, if we say AF, that can be find out from this, right. So, effective area can be find out, then we can find out the depth and thickness, means thickness and width we can find out. Okay. Now, economic depth. In case of riveted jointed plate girder, we have seen how to find out an economic depth. Here also we will find out, that is the gross area first we will calculate, that is AG, which is equal to 2 into C1 into AF plus C2 into D into TW, right. Now, the variation in girder cross sectional area is to be examined as a function of depth, right, of the wave, to find the depth which gives minimum area. That means, we will express the equation for writing the area of the total plate girder in terms of depth, then we can minimize it, right. So, to find out the minimum area, we have to find out the gross area, then we what we will do, we will partially derivative against the depth, right, that I am coming. So, here whatever we are using C1 and C2, because other things we know, AF, D, TW we know. C1 is factor to account for the reducing size of the flange at the region of lower than the maximum moment, right, and C2 is the factor to account for the reducing wave thickness at the region of reduced shear, right. Let me repeat again, what is C1 and C2? C1 is factor to account for the reducing size of the flange at the region of lower than the maximum moment, and C2 is the factor to account for the reducing wave thickness at the region of reduced shear. And as we know, AF is m by sigma BC or BT or B for laterally resistant beam. We can write AF is equal to m by sigma BC or sigma BDD minus AW by 6. So, from this we can find out AG. The value of AG will become this 2C1 into this AF plus C2 into D into TW, right. So, AG we can find out. Now, for minimum depth, for minimum area, what we have to do? For minimum area, we have to make del AG del D equal to 0, right. Del AG del D is equal to 0. So, if we this AG, if we make partial derivative in terms of D, then we can get this value as like this, del D into 2C1 into m by sigma BC into D minus AW by 6 plus C2 into D into TW, right. So, in this way we can find out the value. So, if we further derive, we will get that del D into 2C1 into m by sigma BC into D minus D into TW by 6 plus C2 into DTW is equal to 0, right. So, from this I can find out the value of D, right. So, value of D will become this, that is square root of 6 C1 m by sigma B into 3 C2 minus C1 into TW, right. So, D I can find out from this expression, right. Now, if we assume C1 and C2 as unity, then I can simplify to this, D is equal to 3 m by sigma B into TW. D is equal to 3 m by sigma B into TW. Here sigma B is either sigma BT or sigma BC, right. So, in general, if we see, if the same steel is used throughout, the value of C1 generally varies from 0.7 to 0.9 and C2 varies, C2 does not vary and generally it is taken as 1, right. So, C1 varies from 0.7 to 0.9 when used with maximum positive bending moment, and C2 is not likely to vary and is taken as unity. So, if we put the value C1 and C2 in the previous equation, then what we will get? We will get the value of D as like this, that is 6 into 0.7, say C1 I am putting 0.7. So, 6 into 0.7 m by sigma B into 3 into 1 as C2 is 1 minus 0.7 into TW. So, now if we calculate, we will get D is equal to 1.826 m by sigma B into TW is equal to 1.35 square root of m by sigma B TW. So, D we can find out as 1.35 into square root of m by sigma B TW. Here we got root 3 into m by sigma T. Root 3 means 1.73 into m by sigma B TW. If we consider C1 and C2 as unity, right, and if we consider from practical point of view, this will become 1.35 in place of 1.73, right. So, this is how we can find out an economic depth where the area will be maximum minimum, right. If d, the depth of the wave, is chosen in this way, then we can find out the area of the total cross section minimum. So, d is equal to 1.35 into m by square root of m by sigma b T w. So, in this way you can start, right. Now, other point is self weight of girder. Now, let the weight of girder, let us consider say W as area of the girder into L into gamma s, where Ag is gross area of the cross section, L is length and gamma s is unit weight of steel. So, weight of the girder we can find out W as Ag into L into gamma s, right. Now, if W is the total UDL over the girder of the span, then the moment can be find out WL by 8, right. If W is the total UDL, then M will be WL by 8 or WL square by 8 it will be if we take meter per meter turn, means UDL load, right. And if W is the total load on the girder, then WL by 8 will be the moment. So, from that point of view we have to check now. Now, Ag we know area of means gross area of the section, that is 2 into m by sigma b into d minus Tw d by 6 plus Tw into d, which we got from earlier equations if you remember, right. So, if we further subdivide means simplify, then this will become 2 into m by sigma b d square minus Tw by 6 into d. I am taking d common plus Tw d, and again d as we got earlier, that square root of 3m by sigma b Tw. If we put that value, so from this we can find out m by sigma b d square is equal to Tw by 3. So, this Tw by 3 I can put here, right, to get Ag. Is it clear? So, here considering C1 is equal to C2, we can find out d value, and from there, from that relation we can find out m by sigma b into d square is equal to Tw by 3. Now, if I put this m by sigma b d square here, then Ag value will become like this. If I put this value, then this will become 2 into Tw by 3 minus Tw by 6 into d plus Tw d, right. Now, if we further simplify, finally we will get 4/3 d into Tw, 4 by 3 into d into Tw. Therefore, weight of the girder per meter run can be find out W is equal to Ag into gamma s, where Ag is the area of means gross area of the section and gamma s. So, this Ag we are putting here 4/3 into d into Tw into gamma s, right. So, weight of the girder per meter run can be find out from here. Now, if we put this relation that dTw by 3 is equal to m by sigma bd, then we can write W, this W is equal to say 4m by sigma bd into gamma s, which will become 4 by sigma bd into m into gamma s, because m I am replacing by WL by 8, right. So, W, the unit weight per meter run, I am going to get as 4 by sigma BD into WL by 8 into gamma S. Now, as we know, we have some L by D ratio. So, if we consider L by D ratio as 15 and for FY 250 sigma B as 165 and for steel if we use unit weight as 77, then we can put the values, all these values in this equation, right. Then what we will get? We will get 4 into WL by 8 into gamma S is 77 by sigma B into D, right. Now, again if we see L by D is 15. So, if we put that on also, we will get 4 into W into 15, that is L by D into gamma S by sigma B and 8. Sigma B is 165 and 8 was there. So, now if we calculate, we will get W by 286. So, in this way we can find out the self weight of the girder, means approximate self weight of the girder can be find out in this way, which can be assumed from this equation, that is W by 286. So, now we will see how to design the flange, right. So, the step is the design of flange for welded plate girder. Now, the area of each flange can be find out from this. Now, in case of welded plate also, the maximum thickness of the flange will be where the maximum bending moment is coming into picture. So, here also we can make curtailment of the flanges as per the requirement. If the girder is simply supported along with UDL load, then accordingly we can find out the moment and accordingly we can make curtailment for the different plates to get an economic section at different places, right. So, in the same way we can do what we have done in case of riveted joint plate girder, right. Another thing is welds connecting flange with wave, right. If we see weld connecting flange with wave, now we have to design here, right. So, the welds connecting the flange plates with wave are designed to take the horizontal shear at that level. So, we have to find out first horizontal shear at that level, which can be expressed from this, that is tau H is equal to V A y bar by I, right, per unit length. Tau H is the horizontal shear per unit length. So, we can write tau H is equal to V A y bar by I. Now, here A means area of flange, right, AF, and y bar is nothing but d by 2, that is distance of the CG of the flange from neutral axis, and I is the moment of inertia and V is the shear force. Shear force means maximum shear force we have to see, right. In addition to this, there is vertical load W per unit length. If the vertical load is there, then resistance force per unit length will become QR as tau H square plus W square, because horizontal shear is coming in this direction tau H, and again if the vertical load is there at that point, then it will be W. So, the resultant will become, which is named as QR, that will become square root of tau H square plus W square, right, tau H square plus W square, and tau H is written here V A y bar by I. Remember, this is shear per unit length, not the shear stress, shear per unit length, right. So, and W is also load per unit length. So, we are if we put those values tau h as VA y bar by I, then we can find out QR, the resistance force per unit length, as this, right. So, QR we got. Now, if we consider S as say size of the weld in millimeter, and let us consider allowable shear stress on the shop weld as say 108 MPa, then the strength of the weld per unit length can be find out like this, right. So, 2S plus 0.7 into 108 MPa, right. So, 151 into S Newton per millimeter. So, strength of weld per unit length per millimeter length can be find out as 151 S, and if V is the shear force in Newton per millimeter, then size will become V by 151. So, in this way we can find out the size of the weld also we can find out simply from V by 151, where V is the shear force in Newton per millimeter, means per millimeter length. Okay. So, in this way I can find out the size. Now, the required size of the weld becomes very small in most of the cases. However, a minimum size of weld has to be provided. In practical cases, what we have seen, the required size will be less, but we have to provide some minimum size, right. To save the weld metal, intermittent weld may be used in place of continuous weld. Then we can save some metal weld, and if we do not use the continuously, then we can use, because size will be required very less as stress is very less, right. But smaller and continuous weld is always economical than larger size intermittent weld due to the labor, material and time involved, because skilled labor is a factor which used to increase the cost. For welding joint, as we know, skilled labor is required. So, these are the some other points also the designer has to keep in mind, like labor and material and time. You have to see which one will be the economical, right. The maximum effective size of the fillet weld is limited by the strength of the web plate in shear. So, the maximum effective size of the fillet weld can be limited by the strength of the web plate in shear. So, now we can find out the maximum size of the weld, that is 2 into S max into this 0.707 into 108 is equal to 20 TW. So, from this I can find out maximum S is equal to 0.661 TW or approximately 2/3 TW. So, maximum size simply we can write 2/3 TW, right. Now, we will see the design of intermediate stiffness, right. The size of the welds connecting web with stiffeners depend upon, one is thickness of the web or stiffener, this is one. Second is the requirements to withstand a minimum shear force between each component of the stiffeners and web, and that is given by the formula this V is equal to 125 TW square by H, where H is the outstand of the plate in millimeter. H is the outstand of the plate in millimeter and TW is the thickness of the web, right. So, requirement to withstand minimum shear, this V can be find out from this. Now, if welding is done on both sides in pair, the effective length of each weld should not be less than the 4 times the thickness of the stiffener. Right. Remember, if welding is done on both sides in pair, the effective length of each weld should not be less than the 4 times the thickness of the stiffener. In case of one side, it should be greater than 10 times the thickness of the stiffener. So, in case of one side, this should become greater than 10 times the thickness of the stiffener. And the last part is the design of bearing stiffener. Design of bearing stiffener. So, bearing stiffeners are provided at the location of the point of loads and about at the ends, and their requirements are the same as in riveted girders. So, in case of riveted girders, whatever requirements are there, similarly we can make it. So, these are in short, in very short I should say, the components which we have to know for designing a plate girder as a whole, right. So, all the components I have tried to discuss here, means all the important components I should say, I have tried to discuss here very shortly. Because of shortage of time, we cannot discuss more because number of lectures, total lectures are limited. So, we cannot go beyond certain extent, and this is the preliminary course. So, I have just given some introduction on the plate girder, so that the students have some idea. This gantry girder and plate girder, in fact, we need to know more and more for practical design, right. Now, I will go through one example of gantry girder, of plate girder, so that we will be understanding whatever we have discussed, we can understand properly, right. So, let us go through that example. So, I am going to demonstrate a very simple plate girder example. Because of shortage of time, we will not go all and every details, just the salient features will show here, right. First, let us see the example. This example today I will discuss little, and the remaining part we will be solving in next class. So, the example is that a riveted plate girder is simply supported over an effective span of 20 meter. It carries a UDL load of 80 kilonewton per meter exclusive of self weight. Remember, exclusive of self weight. Design the plate girder completely, assuming that it is effectively supported in lateral directions. So, what is this? That a plate girder is there with a span of 20 meter. So, let us assume we are going to use I section, right. At the beginning, let us means I section type of plate girder we are going to use, right. And so, what other things has been told? That riveted plate girder. So, this has to keep in mind. So, the economic depth etc. will be calculated from the formula which we have derived in case of riveted plate girder, right. So, this is 20 meter and a UDL of 80 kilonewton per meter. kilonewton per meter, right. What else is given? It is simply supported and then it is excluding the self weight. So, self weight also we have to calculate, right. And other things, let us assume that the steel we are going to use, that is say Fy is equal to 250 Newton per millimeter square, right. And say as riveted plate girder we are going to use, let us use say Phi is equal to 20 mm power driven soft rivet. So, these are the two things let us assume. One is rivet diameter as 20 mm power driven soft rivet, and the steel whatever we are using, its Fy value is 250 Newton per millimeter square, right. So, these are the details of the example. So, what are the things are given? Very preliminary things given. One is effective span LE, that is given 20 meter, UDL load W has been given say 80 kilonewton per meter, right, and it is simply supported, right. Simply supported means M will become WL square by 8, maximum moment will develop from this formula, right. So, what we will do in this problem? Let me go through some steps before starting the example. What are the steps will be required to design this plate girder? Means steps means broadly I have just made 6 steps. One is computation of shear force and bending moment. So, very big step in fact we can say, very big means steps are very large. That means first we have to find out the economic depth of the section, right. Economic depth of the section we have to find out, then we have to find out the self weight, because self weight is not given here, because we do not know the section, how do we find out the self weight. So, economic depth is first we have to find out on the basis of formula whatever we have discussed earlier, then the self weight also we will find out, approximate formula is given from which we can find out. Then we will find out the shear force and bending moment, shear force and bending moment. In fact, in case of bridge, the plate girder is used for the moving load. So, in that case again we have to see at what position the maximum bending moment will develop at a particular section, and in that way we have to find out the worst condition and then we have to design accordingly, right. So, first we will find out the shear force and bending moment, then economic depth and design of wave, economic depth and design of wave, then design of flanges, then curtailment of flanges, flange plates, we can go for curtailment, then design of connections, we will go for design for connections, and then finally we will go for design of stiffeners. If we need to provide stiffeners, then we will provide stiffeners also. So, these are the broadly 6 steps we have to follow, right. Now, as time is over, so today I like to conclude this lecture. I will suggest you to work out this example at your home, and then in next class when I will be working through this example, you can check it, then it will be easy to understand properly. So, thank you very much for your patience to listen to this lecture. Thank you.